Now if we go back to S squared, which is the first non-trivial application of this result, so A is 2, what is the forward value of a contract which promises to pay, what is the forward price for a contract which promises to pay S squared, whatever the stock price is, the square of that stock price at time t. And here we have e to the RT, and we just plug in the formula with A equal 2. And we conclude that the forward price for S squared is the forward price for S squared, and then there's a vol factor. So what we conclude is that the forward price for S squared is bigger than the forward price for S raised to the square. And that's because, and we'll see in a moment, of the volatility of stock prices and the convexity of the square function. We get that the forward, write that down, of S squared is bigger than the forward price of S raised to the square, and that's because this exponential is going to be bigger than 1 because we have a positive exponent. How about an A of minus 1? We made no assumptions on A in the derivation, so A can be minus 1. So we now want the forward price for the delivery of 1 over S dollars. So it's going to pay the reciprocal of the stock price at time t. And again, simply applying the earlier formula with A equal minus 1, we get the same result. And what we see is that the forward price for a delivery of 1 over S is bigger than the 1 over the forward price of S. That's what this means. That's the reciprocal of the forward price for S. And the multiplier is, again, the same factor. And the reason that in both cases we get this result, that the payoffs for S squared and 1 over S, that the price is higher, the forward price is higher than if you simply take the apply the function. In other words, what we see in both cases is that the forward value of a function, a forward value of a function of S, in both cases was bigger than the function applied to the forward value of S. Right? This is what we just saw. If the function was square, or the function was 1 over S, in both cases we saw that the forward applied to f of s, and what's noted here is that this is related to Jensen inequality and convexity, and let's see why. If I look at the graph of 1 over S, looks like this, and if I look at the graph of S squared for positive S, looks like this. They're both convex. And now, Jensen's inequality says that if I have any function, the expected value of f of x is greater than, these are strictly convex, but in general it's greater than or equal to, but because these are strictly convex, it's greater than f of the expected value of x. Well, this is exactly what we saw, because the forward value was equal to the expected value of this function under the risk-neutral measure. I'll call it just a star. These forward values, you recall, were expected values under the risk-neutral measure of a function of s. And what Jensen's inequality says is that the expected value of f of x has to be greater than f applied to the expected value of x. Well, and the expected value of x would be the forward value on x. So this is the forward value on f of x, and this is f of the forward value on x. So it's explainable by Jensen's inequality that if we have any convex function of x, that the forward price on that function of s will be greater than the forward price of s, the function applied to the forward price of s. So this is going to be general. What we see here, this is going to be true for any f that's convex. And we saw two examples of s squared and 1 over s. But if s is any convex function, the forward price of f of s is going to be greater than f of the forward price of s.